It's my distinct pleasure to introduce Dr. Pancho Barriga from the Scott Lowe Lab, who's going to tell us about macheting the cancer genome.
Today I'd like to talk to you about cancer genomes and our efforts to try to understand how cancer genomes remove pieces of themselves to allow the tumors or cancer cells to have these very nasty properties. So first things first, what is a genome? Well, a genome is basically the entire collection of instructions that allows a cell to perform its functions. Basically, all the genes. Now, more interestingly for us is how is the genome organized? And for me, the most visual and simple way to think about it is in a Jenga tower. So a normal tissue, a normal genome basically is the Jenga tower right out of the box. Every level has all its pieces nicely stacked, everything fits, it's a very stable tower. Now, when you look at a cancer genome, actually you see the tower is missing several pieces, and it seemingly should be more unstable. But of course, cancer is an excellent Jenga player, and it never really topples over. And they achieve this by cheating. So when you remove a piece of Jenga, you have to stack it on top. Cancer doesn't do that. They remove these blocks and get rid of them. Now, these blocks are actually a metaphor for very large pieces of the genome that contain hundreds and hundreds of genes. Until today, we've been really good at understanding what a single instruction or gene does, but what these large genomic aberrations or these large chunks of the genome do is still really unknown. So in order for us to understand this, I developed a method called molecular alteration of chromosomes with engineered tandem elements, or machete. Reverse engineering that acronym is one of my proudest scientific moments. And basically, what machete allows you to do is instead of looking at a single gene, it allows you to remove large pieces of the genome. And it allows you to do it one at a time. And moreover, it allows you to do it over and over again. So basically what we do is we start with a normal genome of a cell, and then we bring our molecular machete. This machete will allow us to remove a very specific piece of the genome that contains up to hundreds of genes. Now we can see whether this particular piece we removed allows the cell to grow, or it doesn't do anything, or it maybe even destroys the cell. Now, by looking at the endpoint, when we look at a cancer genome, we know all the pieces that are missing, but we don't really know which one did what. So with our machete approach, we can iteratively start playing this game. And now we're actually playing the game cancers play, which is removing large pieces of the genome and not a single gene at a time. So our research has actually found that some of these large blocks are enabling the cells to grow much faster, which implies that in these large regions of the genome, several genes are able to stop this. And more recently, we've seen that one of these pieces is involved in metastasis. So ideally with this, we'll understand how to beat cancer at Jenga and topple over its tower.